Why does pepper sauce make you sweat, but ice cools you down? Or why does light and flambeau give off heat, but dissolving salts sometimes make your water colder?
That, my friends, is chemistry at work. Let's talk about energetics. Hi scientists! Today we're going to talk about energetics, the heat changes in chemical reactions, and why it matters.
Let's talk objectives. By the end of this video, you will be able to distinguish between exothermic and endothermic reactions, explain enthalpy and activation energy, interpret energy profile diagrams, calculate energy changes from data, and finally, appreciate how energetics affects everyday life.
Energetics is the study of energy changes during chemical reactions. Most of the time, that energy is heat. Reactions can either take in heat or give off heat. When we talk about energy change, we usually describe two parts:
The system, the chemicals reacting, and the surroundings, everything else around them. If the system releases heat to the surroundings, we say it's exothermic. If the system absorbs heat from the surroundings, it's endothermic.
Energetics helps us to understand what's really happening in chemical reactions, not just in the lab, but in everyday life. When you eat food and your body turns it into energy to run or dance, that's respiration, an exothermic reaction. When you eat spicy pepper sauce and you start to sweat, that's your body's own exothermic action. When you put on an ice pack on your leg because of injury, it absorbs heat from your leg. That's
Endothermic.
when fireworks explode on Old Year's night, or you light a diya at Diwali time, those are exothermic reactions. When plants take in sunlight energy for photosynthesis, that's endothermic. Knowing what happens with heat during reactions helps us design safer processes, save energy, cook food, and even understand how our bodies work.
Let's look at the characteristics of exothermic and endothermic reactions.
When a chemical reaction occurs, bonds in the reactants are broken, whilst new bonds are formed in the products. But here's the key: breaking bonds absorbs energy. It's like pulling apart two strong magnets. However, forming bonds releases energy. It's like snapping two magnets together. Now let's link this to what we already learned and what you may experience in the chemistry laboratory. In an exothermic reaction, the energy released when new bonds are formed is more than the energy needed to break the old ones. That extra energy flows to the surroundings, so you might feel your beaker getting hotter. In an endothermic reaction, it's the opposite. So it takes more energy to break the bonds in the reactants than what is released when new bonds are formed. So energy flows into the system and you'd feel your beaker getting colder. So anytime you feel or measure a temperature change, chances are bonds are being formed or broken behind the scenes.
With exothermic reactions, heat is evolved to the surroundings, the reaction vessel gets hot, there is an initial temperature increase on your thermometer, and then you'd see a final decrease. The products have less energy than the reactants, and the enthalpy change, or delta H, is negative. For your endothermic reactions, heat is absorbed from the surroundings, the reaction vessel gets cooler, there is an initial temperature decrease, then a final increase. The products have more energy than the reactants, and finally, your enthalpy change, or delta H, is positive. Let's go into energy profile diagrams.
Energy profile diagrams help you see what's happening with energy. Your x-axis is labeled the reaction pathway, while your y-axis is your enthalpy. In an exothermic reaction, the reactants start with more energy than the products, which means that energy is being released. In an endothermic reaction, the products have more energy. Energy was absorbed from the surroundings. The vertical difference, we call that your enthalpy change or delta H. We can also mention your activation energy here on your diagram, which we will explain a little later on. What is enthalpy? Enthalpy is the total heat content of a substance, and we use capital H to represent it. We can't measure H or enthalpy directly. However, during the course of a reaction, we can measure how much it changes. We call this the enthalpy change or delta H, and its units are kilojoules or kilojoules per mole. If delta H is negative, as in the case of an exothermic reaction, heat was released. But if delta H is positive, that means that your reaction was endothermic and heat was absorbed. The enthalpy change of a reaction is summarized by the following formula. Enthalpy change of a reaction is equal to the total enthalpy of your products minus your total enthalpy of reactants, or delta H reaction is equal to H products minus H reactants. Let's talk about activation energy now. So imagine this. You have all the ingredients to make a perfect bacon shack. The dough, the seasoned shack, and the oil. But if you don't turn on the stove, nothing happens. That little boost of heat you need to get things going, that's the idea behind activation energy. Every chemical reaction needs a minimum amount of energy to start, which we call the activation energy, or EA for short. It's the energy needed to break the existing bonds in reactants before new ones can form in the products. You can think of activation energy as pushing a boulder up a hill. You need to push it to get it over the top, then it rolls down on its own. If the hill is too high, then you may not have much of a reaction. But if you have a nice gentle slope, then the reaction will take place more easily. Now you may have heard of the term catalysts before. Catalysts are like helpers. Catalysts are substances that lower the height of this hill or lower the activation energy, thus making the pathway to your products a lot faster. Catalysts speed up chemical reactions by lowering the activation energy, but they themselves are not chemically changed. You may have heard of enzymes in the digestive system, also in catalytic converters in cars, which help to reduce pollution. Catalysts don't affect delta H or your enthalpy change. They just make the path to your products easier.
Calling all scientists, it's quiz time! Let's see how much you are absorbing. Ba-dum-dum-ching! Get it? Let's go! What term is given to a reaction which transfers heat energy to the surroundings? Exothermic, endothermic, reversible, or photosynthesis? You got it! Exothermic. Next question. In an endothermic reaction, heat flows toward the universe, surroundings, system, or thermometer. Right again, it's the system. Let's try one more. What is activation energy? The energy of the products, the reactants, the energy lost in the reaction, or the minimum energy needed by reactants to form products? Yes, it's the really long one, the minimum energy needed by reactants to form products. You did it! Now let's move on to some calculations. Calculating heat change. You need to know what the heat of neutralization and heat of solution is for your CSEC syllabus. Heat of neutralization is the energy change when 1 mole of water is formed from the reaction of an acid and a base,
whilst your heat of solution is the energy change when 1 mole of solute dissolves in a solvent like water. In the lab, we use a simple calorimeter, which is often a styrofoam cup, to measure temperature changes. It helps estimate the heat transferred in or out of the system. To calculate this, we use the formula Q is equal to mc delta T, where Q is the heat energy gained or lost in joules, M is the mass of the solution, usually in grams, C is the specific heat capacity for water, that's 4.2 joules per gram per degree Celsius, and delta T is the temperature change, which is your final temperature value recorded minus your initial. Then we divide Q by the number of moles to get delta H, the enthalpy change per mole. In experiments to determine the heats of neutralization and solution, you'll make 3 assumptions in your calculations. Firstly, the density of a dilute aqueous solution is the same as water. That is 1 gram per cubic centimeter. This means that the mass of 1 cubic centimeter of solution is 1 gram. 2. The specific heat capacity of a dilute aqueous solution is the same as water. That is 4.2 joules per gram per degree Celsius. 3. Negligible heat is lost to the surroundings or absorbed from the surroundings during the reaction. Let's do a quick example of a neutralization reaction using a simple calorimeter. A student mixed 5 milliliters of a 0.1 molar hydrochloric acid solution with 50 milliliters of 0.1 molar sodium hydroxide solution. The temperature increased from 25 to 32 degrees Celsius. Calculate the heat energy released and then find the enthalpy change per mole. So we have 3 main steps. Step 1, we calculate Q. Q is our heat energy. Firstly, I like to start off with our balanced equation. So here we have HCl plus NaOH giving us NaCl plus H2O. And everything is in a 1-to-1 ratio. From our assumptions, we know, or we assumed rather, that 1 milliliter of solution or 1 cubic centimeter of solution has a mass of 1 gram. So when we add up our 2 volumes, 50 and 50, we get 100 grams of solution. Our specific heat capacity of 4.2 joules per gram per degree Celsius holds here. The temperature change is our final value, 32 degrees Celsius. Take away our initial, 25 degrees Celsius, we get 7 degrees Celsius. Plugging the values into our equation, we get 2,940 joules, or dividing by 1,000 to get kilojoules, we get 2.94. Step 2, we calculate the moles of limiting reactant. In this case, however, our acid and base are in a 1-to-1 ratio. They have the same volume and the same concentration. So in this case, it really doesn't matter. Moles is equal to concentration by volume. That's the equation that we will be using. So just pulling from HCl's values, we use 0.1, which is the concentration, multiplied by 0.050, which is the volume that we converted to liters, we get 0.005 moles. Step 3, we calculate the enthalpy change per mole. From the question, we saw that there was a temperature increase from 25 to 32 degrees Celsius. Therefore, that tells me that we have an exothermic reaction. Therefore, our solution, or our final answer rather, should have a negative value in front of the answer. Delta H is equal to Q divided by number of moles. So we take that 2.94 kilojoules from part 1 divided by 0.005 from the second part, and we get 588 kilojoules per mole. Since it's an exothermic reaction, we put a negative sign in front, so we get negative 588 kilojoules per mole. So let's recap what we've learned today. Energetics is about energy changes. Exothermic reactions release heat, whilst endothermic reactions absorb heat. Activation energy is the minimum amount of energy needed to start a reaction. Catalysts, they lower this activation energy, causing more frequent effective collisions. And energy profile diagrams, they map out energy changes in reactions. And the next time you're eating a hot doubles and start to sweat down the place, just remember, energetics is at play. Keep exploring.